My name is Brian Will. I'm a software architect in Intel's network processing group, and I work on QuickAssist Technology. So what I'm going to cover today is a product, the QuickAssist product, which is an accelerator for cryptography and compression. But specifically today, I'm going to look at the integration of that in with OpenSSL and with nginx, and kind of the performance improvements that you can see by using acceleration, and some of the features that are coming into both OpenSSL and nginx that enable that model. So first of all, I'll just have a quick look at the market trends, what's pushing security, what we expect how we expect to see it going into the future. I'm then going to hit an overview of QuickAssist for those that aren't aware of it, and then get into physically the results and the changes that we made to get these kind of results, and where people can get them. So market trends. So if you look at Sandvine, more encrypted traffic is coming into the future. So if you look at the current 70% of the internet traffic in North America and Latin America is encrypted. And a lot of that is being driven by, you look at video content on the web, it's a huge component of the network traffic, and that's all moving to encrypted forms as well. So all of your video transfers will start to happen over SSL and TLS. Mobile is growing at an alarming rate, and that is also driving heavy loads of encryption. There's also a move toward encrypting the internal data centers. So generally the trends you're going to see is on the web, everything will be encrypted. Internally in your data centers, everything is trying to move to an encrypted model as well, rather than just at the edge. So generally the trend will be toward more encryption. The other trends that kind of affect this is you're seeing things move from kind of just physical appliances to kind of hybrid and more software-defined infrastructures and networks. What that physically means is, like, if you look at say a very typical deployment, it would have had kind of a box that would have been dedicated as a top-of-rack switch that would have load balanced out to the back-end servers. The SSL termination would have happened at that point, and then everything internally would have been in clear text. What you're seeing things move toward is move that appliance out into a software component or a software-defined component that can now act as a load balancer behind, say, common centralized services, so that you can have, instead of having one dedicated rack or one dedicated data center to do this, you have blocks inside of your data center that serve different services. But as well as that, you have encrypted connections going to the back-end services as well. So encryption in, encryption out. So if you look at a reverse proxy, it's going to be encrypting on both ends of that link. And they have slightly different characteristics, those two links, but that's kind of the general trend. So resources will be then brought into kind of a pool type architecture where they're given out to the applications and used through orchestration layers. So QuickAssist itself is an accelerator for crypto. The easiest way to describe it is it's an accelerator for crypto and compression. Specifically, it's an accelerator of asymmetric cryptography and bulk encryption and compression. So on the compression side, we support deflate, zlib. If you're not used to the standard, we support deflate, compression, decompression. And on the bulk encryption and PKE, we support your whole host of crypto algorithms that you'd see for SSL, IPsec, storage, and so on and so forth. And I have a list of all the algorithms in a minute. QuickAssist comes in three form factors. It can come as a chipset, so the physical device is embedded into the chipset, and it comes as a chipset for a range of processors. You can get that as a PCI Express card, physically a plug-in card, and there's a number of vendors for that card, or you can get it as an SoC. So if you look at our C2000 range, the QuickAssist is embedded into the SoC complex. So essentially, QuickAssist will integrate the hardware acceleration compute for crypto and compression into the Intel architectural platforms, either by one of those three methods: chipset, PCI Express, or SoC. Now, I won't go through this in detail. Everything on the left-hand side of the slide, I will not cover. I'll let you guys read it if you're interested. But essentially, we cover a gamut of algorithms. These are the typical algorithms you're going to use for either TLS, IPsec, disk encryption. This also covers the asymmetric, so the SSL handshakes for RSA, elliptic curve, Diffie-Hellman, DSA. On the right-hand side, I will cover this because this is going to be important numbers to remember when we get to the actual performance graphs and the benchmarks that I'll be showing. But if you look at this, say RSA-2K decryptions for the 8559 device, you can do 40,000 RSA-2K decryptions per second. If you look at, say, a typical TLS handshake, there's kind of 3 standardized handshake algorithms or sets of algorithms. There's RSA-2K, there's elliptic curve Diffie-Hellman ephemeral with RSA-2K, or there's elliptic curve Diffie-Hellman ephemeral with ECDSA. And if you look at those, we can do 17.6 thousand operations per second for elliptic curve with RSA, and elliptic curve with ECDSA, we can do 20,000 operations. That's the device capabilities. And then as you see from the symmetrics algorithms, we support AES, TLS, RC4, but AES, SHA-2, and the various modes of those algorithms. So this is really targeted at IPsec, SSL, TLS, and also kind of encryption and some deduplication applications. I'll go very quickly on this, just so you know the capabilities of QuickAssist. It also has data compression. This is all based off the deflate algorithm. So deflate is a combination of LZ77 and Huffman encoding, and it's what you would see in standard zlib. So we support adding headers of both zlib and gzip, and the device can do 24 gigabits per second of deflate compression and decompression. This is targeted at big data applications, WAN acceleration, HTTP compression, and file systems. There's some more advanced features that we also have support for. Again, this is connected over PCI Express. So if you wanted to do something like, say, for disk encryption, where you wanted to encrypt and compress the data, that can actually happen in one traversal over PCI Express. We can do both of those operations down on the device and hand back an encrypted and compressed block. We also have other features like batch and pack, which kind of enable seekable compression in a deflate standard. So on to the physical benchmark and the results. So the benchmark is quite simple. We basically take nginx 110. We connect that up with OpenSSL 110, which was released about 2 weeks ago. And we connect that up with an engine that we've written for the Intel QuickAssist Technology that plugs into that on a standard Linux. It's a CentOS distribution that we use for this benchmark. All we do is we create a HTTPS connection. We use 3 different certificate types. So we use RSA-2K, elliptic curve Diffie-Hellman with RSA-2K, or elliptic curve Diffie-Hellman ephemeral with ECDSA. And we physically make the connection and close it down. So really what this is testing is connections per second, and there's no keep alive, so it's physically doing all of the crypto operations and all of the handshakes for every single connection. So as kind of the bottom part of this says, 0-byte file transfer, RSA-2K. From the elliptic curve standpoint, it's doing the P256 curve. And this is all TLS 1.2, and the cipher suite's AES 128, CBC, HMAC, SHA-1. So the results. So there's 6 set of bars per core combination. So the way we've constructed this benchmark is you limit to a core combination, and then you drive the software and the accelerator to the max performance that they can get within that core combination. And then what we did was we scaled up the number of cores to the point where we hit limits. Specifically, those numbers I was telling you to remember from before, the limits of the hardware device and where we can hit those limits. There's 6 bars per kind of core combination. The green are all hardware accelerated with QuickAssist, Intel QuickAssist. The blue is OpenSSL 110 software, and it is highly optimized software, but it's OpenSSL 110 that you would just download off the GitHub repo. If you look at, say, the dark green bar, this is using OpenSSL asynchronous features, which I'll go into in more depth in a minute. But this was features that we worked with OpenSSL to get into 110. And this is kind of utilizing some of the characteristics of having an accelerator available. So as you can see for like the dark bars, RSA-2K, a rough estimation is that you're getting about 5.6 times improvement in connections per second. So within the context of 10 cores, you can actually handle 40,000 users, is one way you can look at it, 40,000 users per second connecting to your web server with an RSA-2K certificate. If you look at the elliptic curve, again, if you remember from the previous slide, elliptic curve Diffie-Hellman with RSA-2K, we can go up to about 17,000 connections per second. And you can see that at about 7 cores, we're hitting 17,000 connections per second for elliptic curve Diffie-Hellman with RSA-2K. and for elliptic cryptophielman is ECDSA. Actually, the RSA2K is slightly a lower number of cores. If we compare and contrast that to the standard software, in an RSA2K case, a single core can do about 800 to 900 connections per second, and you compare that to about 4.9,000 to 5,000 connections per second using the accelerator. Now, there's a few reasons this is possible. So again, the hardware can do these decryptions very fast. It can do it at the data rates shown. But again, there was a number of things in the software stacks that we had to implement to add this asynchronous type behavior. The other thing to note is that both of these scale quite well as you add cores. And the way we contextualized this was to say, this is using an entire core in each of these cases. So if I say a 10-core number, we're utilizing roughly between 90 and 100% of that core to do that operation. So the way you can look at this is look at the data point of the connections per second that you need for your application, and then map that down onto the platform that you're using, and those will be the cores that you have left to deal with your entire application processing. So the way we're able to get this type of performance gains is through something we added into OpenSSL called asynchronous processing. If you go onto the OpenSSL website, and this was a joint piece of work between us and OpenSSL. If you go onto the OpenSSL website, it's called the job infrastructure. But first of all, I'll just describe what asynchronous means because it has a few different connotations, and I'll just describe what I'm terming it to mean. So in a fully synchronous model, you would call into an API that would block, and you would then sit pending, waiting for the response to come back. What that means is that in order to parallelize work, you have to use something like threads or process context switches so that you can actually run multiple jobs in parallel. So when you have a hardware device that has massively parallel capabilities underneath, you need some way of parallelizing it. And those context switches and thread switches are actually costly if you start to do that and scale that upward. The other way of doing it is actually posting jobs, having the stack actually realize that there's other work that I can do in this period of time, and then let the stack process something else while you're waiting for the response to come back in an asynchronous fashion. So what we added was a framework into OpenSSL to allow SSL contexts, or specifically to translate it into what happens is an SSL connection, to run asynchronously with respect to all the other SSL connections or with respect to anything else running in the system. We did this work on OpenSSL. By rough estimate, about 66% of the active websites are currently using OpenSSL. That was a report from 2014 from Netcraft. You could probably take it that that's, I don't know which direction that's changed, but again, OpenSSL is still a very predominant stack within the market. It's probably gone up at this point. If we look at the new features that were added that are associated with async, so probably the biggest feature that was added was the job infrastructure. And the one way you can think about the job infrastructure is if you're familiar with fibers or coroutines, essentially a job is a fiber or a coroutine. It's probably more like a coroutine. So it's not a scheduled entity, as in it's up to the application or the user to schedule those events. And that gets implicitly done through the SSL APIs, as you call them. But what it does is it provides a way of recording the stack where you've executed to, the variables on that stack, and then it provides you a mechanism to switch out and start doing other processing. To add to this, we added event notifications. So again, you needed some way of knowing when to start reprocessing that coroutine, or when to start reprocessing, I'll use the terminology in OpenSSL, start processing that job again. So we have full event-based support built into that job infrastructure, so you get told when work is done, when it's time to wake it up and start doing that work again. And then the stack is developed in a way that it can run either synchronously or asynchronously. So again, we have to make sure that this thing works for all applications. So 1.1.0 will still work with your existing applications. There is work to port over to the new interfaces in 1.1.0 where all the data structures were made opaque. That's just using the proper interfaces, getters and setters. But if your application can't harness asynchronous, it can still run with 1.1.0. It can still run with QuickAssist. It just can't get the performance gains. And this is a capability that you can actually choose on a per connection basis, and you just set a mode on the connection to say I can run synchronous or asynchronous. And then finally, we have this other feature called pipelining. And really what this is it takes SSL records that from a cryptographic standpoint are independent and allows those records to be pipelined into the engine in OpenSSL or the device. So what this means is you can push a number of records down to the device to be encrypted in parallel, and those will be received back, ordered, and put back into the sockets in the OpenSSL stack. Now, what's the value of async? So what we were trying to do here was to concretely show the value of adding async support into the OpenSSL stack. So what we did was we did 3 kind of benchmarks. The blue is standard software, so that's going to run synchronously anyway. The orange is running synchronously with hardware acceleration. Now, the configuration in this, I'll say up front, the configuration of this stays constant across each of these. So we could configure this so synchronous will be better by increasing the number of worker processes per core and driving up the number of context switches that happen. Again, you're going to run into a context switch bottleneck as you start to do that. But just for demonstration purposes, we kept everything nice and constant. So this is a mapping of 1 worker process to 1 logical core. And then the green bar is with asynchronous and with acceleration. So as you can see, asynchronous above software, as we previously mentioned, is giving you about a 5.6 gain. But asynchronous over synchronous is giving us about a 3.9 times performance improvement across the operations. This was using RSA 2K as the example. So again, what you're doing is you're essentially running these jobs. You have a parallel processing unit. You're essentially running these jobs in an asynchronous fashion outside the context of the overall application. The application gets those cycles back to process new connections in this case, or it could be processing application workloads while that crypto operation is happening in parallel. And then it'll get a notification back to tell it when to switch. The job framework that's in OpenSSL, as I said, it was kind of like a fiber or a coroutine model. So essentially what's happening here is you have a number of operations that can be in flight. So what I did was I took a very contained example. So I took at the EVP API if you're going to do an RSA sign operation. Just 1 operation, and then you wanted to parallelize that. So what you do is you can run an RSA operation, and you grab a job, and you say, in the context of this RSA operation, I want to run in the context of this job, I want to run an RSA operation. That gets posted off to the async infrastructure and eventually works its way down into the QuickAssist engine. The RSA decryption will happen, and essentially at the point where we submit the work to the hardware, we call what's termed a pause inside the job infrastructure, which causes a context switch or a fiber swap. And these are using the low-level primitives of POSIX, make, context, get, context, set, jump, long jump, to actually manage those context switches. So it isn't your threads or processes. This is fully managed inside of the OpenSSL stack at a very low level. These contexts are not schedules, as I said before. The scheduling occurs inherently by the application calling those external interfaces. So the action of pausing out gives a notification back to the application that called at the EVP API saying there's an async wait event that you need to block on, and here's a file descriptor. You throw that file descriptor into an epoll. When that file descriptor fires and you get your event, you simply call RSA sign again. It knows that there's a job associated with that sign operation, and it switches back into the engine to pull the result and process that back up to the application. So that's at a low level. That's at the EVP API. If you can imagine all of the SSL external APIs, SSL write, SSL read, SSL handshake, all of those now have job support. So essentially, they're aware if you're running in a job context when you call them. And the next time you call them with an active job, they will cause a fiber context switch on that job and bring you back to the location where the stack paused you. So just to kind of reiterate, that's how we're able to get these kind of performance gains with asynchronous. Because essentially, in the shadow of where we would typically block, we can actually parallelize a number of operations down into the device with 1 context. So we don't have the context switching overhead when we run asynchronous because the contexts are actually managed in OpenSSL at a very low level. For Intel QuickAssist, we have an engine available. It's on GitHub. This is the algorithms and features that it currently supports. So you'll see, like on the PKE offload side, we support a large list of algorithms. And on the symmetric, so your common suspects, RSA, elliptic curve Diffie-Hellman with ephemeral, ECDSA. So that covers your kind of common negotiated cipher suites for TLS. It'll also cover most of the other algorithms that you need. If you were doing, say, an IKE using libcrypto and user space, you could also use those. From the symmetric side, we cover, today, we cover 4 algorithms. And we call these chained operations. So this was another feature actually that I didn't have on the list that is in 110, that any things that can look like an AED cipher or that can be chained together, we can chain those together as an operation inside the engine. So if you look at like AES 128, CBC, HMAC, SHA-1, that actually goes as one request down to the engine and one request down to the hardware because those can be done in parallel in the hardware and chained as one operation into the hardware. So today we support AES 128 CBC, HMAC, SHA-1, AES 256 variant of that, and then we support the SHA-256 variants of that as well. Another feature that got added into 110 is the ability to offload pseudo-random number generation. So if you don't know the SSL handshake very well, you probably don't know what this is, but it's an intrinsic piece of the SSL handshake where it randomizes a data value that's negotiated between client and server, and that's used, it's an intrinsic piece of the data sharing that happens in a handshake to come up with your symmetric keys. That operation is what I call a compounded HMAC. So essentially, it's one piece of data run through a HMAC into another HMAC into another HMAC until you produce enough data to actually create this random field. And it's quite costly. So this also gets offloaded to the engine as an operation. It supports, the algorithm is different for SSL 11, 12, and 30. All those get offloaded to the engine that we have in QuickAssist. One area that we're still working on is pipelining. So we have pipelining support that we've developed internally, and we're going to be releasing that out very shortly. We're still working on some more optimizations when we hook that into the application layer. So if you think about OpenSSL, there's kind of 2 levels that you can benchmark things at. You can what's called OpenSSL speed, so you can benchmark at the libcrypto and just the crypto layer, and then you can also benchmark at the application layers such as nginx. So the pipelining we've got fully working at the speed level. We're also trying to integrate that into the nginx level, and that's kind of our next activity. So I suppose the one takeaway from this is you can expect future features to continually come into the engine. We're going to keep working on this for a while. Now, the modifications needed in nginx. This is currently our nginx patch is not, we haven't posted it publicly, but we expect to get that available quite soon. And really, there were very few changes that we needed to make in nginx. So nginx already had this very asynchronous event-based architecture, which suited this type of optimization very, very well. The changes that we needed to make inside nginx were reasonably small, and they were focused on one aspect. It was the fact that nginx was never aware that an SSL connection could have an event. Typically, the events that it would look at were sockets, maybe file descriptors, but it wasn't an SSL connection. And the difference now is that an SSL connection can actually have an event associated with it and can wake up a piece of work. So kind of a very quick summary of the changes that were made is, as you start to run a connection in nginx now, it can get an error return back from all the SSL APIs. That error return is basically going to tell it, put me back in your event loop, and oh, here's a file descriptor to put in that event loop. And when you get that event on that file descriptor, wake me up and call that SSL API again, because there'll be a result there. So while there were a number of changes that we had to make, they were all quite small, because the overall infrastructure already supported this concept of asynchronous. Because one way you can think of asynchronous is it's very much like a non-blocking socket. The paradigm is very close. So essentially, we were extending that to also encompass SSL connections. So in the nginx config, you have this ability to turn async on and off. And again, that's to handle applications that may not be able to take advantage of this asynchronous nature. It's really just if there's concern, you can actually turn it off per server block inside of the SSL config file. We made changes in the nginx connection, and this is really around making nginx aware that there's a file descriptor now associated with an SSL context or an SSL connection, and that it can fire. So this needs to be put into the epoll loop. And there's typically one SSL context. There's some corner cases that you would get multiple file descriptors per SSL context, but realistically it's going to be one because the only way you get multiple is if you have multiple engines loaded at the same time. And then you have nginx event notifications. So this is really taking those job FDs that we talked about, adding those into the nginx infrastructure, and really hooking those into the top level epoll file descriptor instance. And then finally, SSL connection events. And this is, we spend a lot of work on this. Intrinsically, we couldn't change the OpenSSL APIs dramatically to support async. So the OpenSSL stack is now aware of jobs. And because it's aware of jobs, essentially all the application needs to do is resubmit to get work. So all of those existing OpenSSL interfaces that you might know are still there. They don't actually change. Their signatures are the same as they would be sync and async. The difference is that they're aware on a per context basis whether you created a job. And because of that, they are also aware that when you call back into them, they need to switch into that job to find those results. So again, that was another reason we didn't need to make any dramatic changes to nginx, because the API stayed exactly the same. All we needed to do was reinvoke them and handle a slightly different error return from SSL get error. So, in summary, as you can see, there were vast improvements in the HTTPS connections per second that we showed. All of this code is available currently today, except for the nginx work, and we're going to be working on getting that available as well. The hardware is available, and what I've listed here is kind of some of the resources. So if you want to get the drivers and those pieces, they're available on 01.org. We've got a GitHub repo for our engine that supports OpenSSL 1.1.0, and it should be as easy as pull down OpenSSL 1.0 release, load the engine, and QuickAssist will be there. There's no longer, we used to have a patch for OpenSSL and we used to have our separate engine. There's no longer any of those things that you have to do. It just works transparently. And you can get more information on QuickAssist if you go to intel.com QuickAssist. And there's a few, at the very bottom, there's some talks that we did both with OpenSSL and a talk on some of the optimizations similar to this, but very much catching it at the top layer, what we did for 1.1.0 and just some of those optimizations. So thank you for your time. I think we have about 10 minutes left, so I'm open to any questions. Yes, well.
I see your ECC and RSA numbers. ECC with ECDSA, the numbers are pretty low with how much of optimization we can get compared to the traditional ones which we use today. It's like 1.25x.
Yes.
Why is it low for ECC? With industry moving towards PFS, shouldn't that be the benchmark and not RSA?
So yes, and all three of them I think should be the benchmark. But you're right, our EC Diffie-Hellman and ECDSA are low. We're still optimizing them, essentially. We would expect those performance numbers to come in line with ECDHE RSA 2K. There are a number of optimizations that we're doing right now. One is around the coordinate systems that are presented to our interface. Basically, you can find our Jacobian coordinates for elliptic curves, and essentially we're adding support to handle both. And there's a few other optimizations around how, so the difficulty with elliptic curve, RSA is one operation. So if you look at the SSL handshake, RSA is going to be an RSA decryption. If you look at elliptic curve, it's actually 3 cryptographic transforms. It's the Diffie-Hellman phase 1, phase 2, which are called compute key and generate key and compute key. And then you've also got the sign operation of the RSA 2K or the ECDSA. So in both of those cases, they're going to be lower performance than the RSA 2K. But that interaction of having 3 asynchronous events in a handshake, we're working on optimizing that path. So I suppose, and I should have mentioned it when I went over this slide, for EC Diffie-Hellman ephemeral ECDSA, expect that to increase. We have some optimizations in the pipeline, we just didn't have them ready for the conference. I think that was the next person that had their hand up, so yeah.
When you're measuring the sync
So that's an interesting question as well. So the CPU utilization in the asynchronous case is between 90 and 100. The CPU utilization for the synchronous case is probably going to be around 70. 70 to 80 is what we usually drive it to. In the synchronous case, it also doesn't have event notifications. So the difficulty there is that you have to pull. So you end up consuming more cycles than you should have anyway, because you're continuously polling to see if that response is there. Now, if we were to take, and that's what I was kind of alluding to in the synchronous versus asynchronous, there's optimizations you can do in the synchronous to bring that up. So one of the easiest optimizations is assign more than one worker process to a logical core, and that will start to drive the performance up. But that will also, you've only got about 30% extra CPU to consume with context switching, so it'll push it up, but it won't push it up dramatically. The other optimization is you could add like event-based notifications so that you can reduce those CPU cycles, and then you can add more context switching. So that's a good observation. You can definitely increase the synchronous performance. It won't get to an asynchronous type model, but you can increase it.
What does it do? What can be like, you increase the best asynchronous versus the best synchronous. What will be different? 30%, 50%?
I don't have those numbers. We didn't run that benchmark. I've run pieces of that benchmark, but I haven't run those two optimizations together.
Is it possible to use the engine, let's say, for some of the operations, the RSA upload, for example?
Yes.
And use the software, the CPU, in OpenSSL to do the EC?
Yes. So we've set up the engine so that you can compile it to choose which algorithms you want to offload. And the engine framework inside OpenSSL, essentially you register as a provider for those operations. So if you don't register, it will call the software algorithm.
So it's a compile thing, it's not a runtime?
It's a compile thing. Because essentially inside OpenSSL, it hooks up the function descriptors to where it can go to get the work done.
How does a QuickAssist compare to what Amazon currently has in support on their EC2 instances?
How does it compare?
Yeah, so last year at the reInvent, Amazon announced that Intel, they're now running their EC2 instances with Intel optimized for encryption offloading.
Okay.
And I'm wondering if the QuickAssist
Yeah, I honestly can't answer. I haven't run on the EC2 instances, but that will be a question I'll bring back. I honestly don't know.
For the throughput memory provided, like can I do 20 gig IPsec and get another 20 gig SSL termination at the same time, or are those numbers independent of each other?
So from the raw performance numbers, the DH8955 can do 50 gigabits per second. So if you wanted to do 20 of IPsec, 20 of SSL, you still have 10 headroom. You can do both at the same time. But the chip has 50 gig of overall throughput that it can provide. So yeah, you can split it out any way you want.
Just a follow-up question too on that. You mentioned that in the absence of using events, you have to use code because you modified OpenSSL to have a job queue now. I thought you said that in the absence of when you chose synchronous versus asynchronous,
Yes.
you have to code.
Yes.
And that's the part I'm not sure. Is it because you already modified OpenSSL to have a job queue?
Well, OpenSSL has a job queue in it now in 1.1.0, but the difference is, so you're in user space, and this is a physical device. So there's no way for the physical device to tell the user space process that something is available, other than like the typical method would be through a file descriptor through an event, or to block on something. And if you block on something, you need something to unlock that. So there's kind of two ways of doing it. If you're going to do it purely from user space, you have to keep polling to see if a response has become available. The other way of doing it is you physically call into like the driver through an ioctl interface where it's blocked on a semaphore, and you physically use an interrupt in the driver to release that. So I suppose the comment I was making is that if you don't have the event infrastructure, which is kind of how we drive, say, the same thing as an interrupt in user space, you physically have to poll to figure out if they're response, if you're doing everything from user space.
Is there a DPDK integration
So,
for user space stuff?
so DPDK now has access, or DPDK has now released CryptoDev, which supports QuickAssist.
What does it mean? How? Maybe I'll talk to you.
Yeah, we can go into the details.
Are you going to provide support for non-OpenSSL libraries like LibraSSL or something more lightweight, or it's strictly going to be OpenSSL?
So at the moment, it's OpenSSL. We're open to providing support across the board, but at the moment, we just have the software stack for OpenSSL.
What's the cost per PBS?
What's the cost?
Based on hardware, whatever we add on top of it?
Well, so the hardware can do so it's very hard to answer the question of what the cost is because if you measure it in CPU cycles, it's only 300 cycles to submit a request. So per RSA operation, it's going to be about 300 cycles. And then the device can handle 40,000 operations per second. The physical, if you were to run one operation and physically take like the timestamp per round trip, I don't have that number at the top of the SSL stack.
So you mentioned that your QuickAssist driver runs completely in user space. So there's no interaction
For data path.
for data path. And there's no interaction with the kernel-based Linux crypto framework or crypto-dev layers which use IOCT that you mentioned.
No. The user space driver for QuickAssist is entirely user space, except for the PCI enumeration and bring up of the device. The full data path is from user space. We also have integration, so the QuickAssist driver is also upstreamed into kernel.org, and it's also plugged into LKCF.
Okay, so have you tested this OpenSSL with the crypto-dev engine, which essentially provides IOCT interface to the Linux crypto framework?
No, I haven't.
What's the time frame for your optimized
I don't have time. Let's put it this way, we're actively working on it now.
like 6 months, a year, roughly?
No, it should be much less than that.
Okay.
It should be much, much less than that.
Is it the same chip or is it different firmware altogether?
No, it's the same chip. It's the optimizations I was talking about there are software. So it's physically the interaction between our engine, the device driver, and OpenSSL. So these are all things that we can implement. And our current trend has been, we've been kind of releasing a new engine fairly frequently with new features, like kind of every 2 weeks.
But these numbers are fairly close to your chip max, right?
For RSA, they are. For elliptic curve and all those, they are. What you're going to see is, with our optimizations, is that it takes less cores to get the max. Essentially, all of our optimizations are going to improve the cycle cost for offloading that operation or for transacting that operation. So what you're going to see is everything shift down to lower number of cores. RSA is probably not going to change. Elliptic curve diffeomorphism and RSA will roughly be about that. The ECDHE, ECDSA, I'd expect to shift.
Small question, like you show a lot about the public, what about bulk operations?
Yeah, so the main reason I don't have the bulk encryption up here is that we haven't finished our pipeline work. The pipelining work, in conjunction with bulk encryption, we should expect good gains. But I don't have numbers. I have numbers on the old stack where we implemented asynchronous very differently. And it's probably not comparable to this. So I won't say any numbers yet because I'd prefer to get it on the newest stack. And again, with bulk encryption, it depends on the algorithm you negotiate to. Well, so the buffer size for TLS, a lot of the time it's going to be 16K because that's the max size, unless you start to negotiate it down to something like 2 or 4K for responsiveness. Again, those buffer sizes are big in comparison to what you're transacting across PCI Express. So the buffer size has an effect, but in the TLS space, it's not as bad as, say, if you were looking at like IPsec with 300 byte packets. The real difference is going to be if you do things like AES GCM or AES SHA. GCM with ASNI instructions is exceptionally fast. Okay.
Is there a way to use this with boring SSL or LibraSSL?
It's a good question. I honestly don't know the answer. But from the fact that both of them were forked from OpenSSL, and I believe, last time I looked at boring SSL, it still had the engine there. And I believe LibraSSL still has the engine there. They should work. Now, the question is, I don't know if, and I haven't looked at those projects in a very long time, I don't know if they're going to take from OpenSSL 1.1.0 and grab the whole async framework. And if they do, then it should just plug in underneath the engine layer. So at the moment, the only QuickAssist changes we make to OpenSSL is underneath the EVPA API and specifically in the engine registration mechanisms inside OpenSSL. So it should work, but I have not tested it. Okay, I think I've run out of time, so I'll close up there, and thank you. Thank you for your time.